start by thanking the organizers for this conference. It's really a wonderful thing to see so many people from the Sacramento area come together from the community colleges. And what is mentioned here was that for a while I was the lead faculty for the impact project in mathematics, which was a project that was supposed to help California improve the articulation, including the community colleges and the public university system. And it was unfortunate that it shut down, but I was very thankful that during that time met many faculty from the community colleges and organized conferences locally to try to encourage regional activities in mathematics between universities and the community colleges. So I'm thankful to see also that there are other people from the university system, at least from CSU here. I hope that we'll continue these things in the future. We'll invite faculty from the UCs and the CSUs to participate with you. I'm going to talk today about calculus. The previous speaker spoke about calculus, and I think mine's going to be quite different. I'm going to try and tell you how I approach calculus in what I think is a sensible fashion, using differential equation, estimation, and modeling in all of the courses that I teach about calculus. And in particular, we're going to focus today on how to understand the fundamental theorem of calculus and the definition of the definite integral, which is what is at the heart of that theorem, in a sensible approach. So, first a little review of what's happening in your calculus course or in our calculus course in the first year. So there's start off with differential and integral calculus, a variety of theory and applications in differential calculus. You have derivatives and applications. You spend a lot of time on things. You do things like regulated rates and Newton's method, and you mix up some theory about differentiability and continuity, and some slight mention of differential equations in the first semester. And then you move on to integral calculus, and you do area, and then magic, fundamental theorem of calculus. So then in the second semester, which I will call Calc 2, some people here are quarter systems, but I think most people are semesters now. So in Calc 2, there's more applications and methods of integration, and then suddenly a whole new world opens up, and the students are in shock for a while about sequences and sums of numbers and theory and tests. All of a sudden you're testing for things. You never tested anything before, but all of a sudden now you might have tested for continuity, but basically everything was compute, and all of a sudden now you're testing and more theory, and then finally you get the power series. If you use Stewart's book, it takes quite a while before you eventually get the Taylor theory, the Taylor series, and then you're actually doing something with this stuff, which is estimating some numbers, estimating some definite integrals, and maybe solving some differential equations using series. Okay, so a little critique here. There's when you get to that sequence and series stuff, although there has been stuff done in the first semester that might be related to it, none of that is used to motivate the work in the series. So you don't look at Newton's method, which is a sequence problem. You don't look at estimations for the definite integral, which is, again, using some sums to estimate a number. And you don't use anything about solving differential equations in that series. So you do this lengthy testing of convergence, and that just delays the connection to the previous course, which is Taylor's theory. And this, at the end of the course, if that's where you finish the course, you have a pretty muggy look, a statement about what's really fundamental about this calculus. Okay, so the sensible calculus, as I teach it, came from an experience 2 years of teaching the second semester of calculus at Bard College with students who had had the first semester with another instructor. And at that time, I came in and the first semester instructor had done the fundamental theorem of calculus, and I just did odds and ends, and I was a lucky teacher because they couldn't make sense out of anything I was talking about because it didn't tie together. The first semester that was bad, the second semester, of course if you're teaching in the second semester and you taught the first semester, they believe you're a pretty good teacher because you just gave them the fundamental theorem, which was so beautiful. And then they can tolerate the fact that things fall apart later on, because they knew it wasn't you, it was the book. But if you're coming in on the second semester, that is absolutely the hardest course to teach in the curriculum for the lower division. In the community colleges, that's the hardest course that you have to teach, Cal 2. And if you're coming in and you didn't teach the first semester, you are getting the bad reviews, I think, that you deserve. No, that you don't deserve, but you get them anyhow because the students are not trained to understand the difference between what they're taught and what their teacher is trying to do for them. So they get the confusion that you have to teach because that's the way the books are organized. Anyhow, after that experience, I came to some conclusions about how to connect the second semester to the first semester, which was to give a thematic approach to the whole year. And the themes that are concurrent for the whole year, there are 3 of them, and I actually wrote this up in an editorial in 1990 that appeared in the UMass journal. It's called Essential Calculus. And the 3 themes are differential equations, estimation, and mathematical modeling, which I spelled with 1 L here. Okay, so the differential equations, of course, that's what you're starting the course with. You're learning about derivatives, so you can talk about differential equations, although you call them derivative equations, they call them differential equations. So it's really nice if in the first semester you actually mention the differential. A lot of people don't want to talk about differentials anymore. You can see the lower level that that's gone because now they want to talk about linear estimations and occasionally mention there's a thing called a differential. But linear estimations are a nicer way to say it, and you don't have to make sense out of the whole notation about the Leibniz notation. What's the dy dx mean? And is it a quotient or isn't it a quotient? Well, it is, but it isn't. It's also confused by that. So if you don't feel comfortable with differentials, of course, then you're going to spend less time on them. You're going to spend less time on linear estimation, and you're not going to. And when you get to differential equations, you'll never know why they're called differential equations. You'll think, oh, they're derivative equations. Oh, we call them differential equations for some stupid reason historically. Okay, but the differential has a lot of meaning in advanced math, and the engineers and the physicists love differentials. And so I think it's to benefit of our students if they're going to take courses outside of our discipline, and we have physics and engineering students in our classes, to say something about the differential and make some sense of it. So differential equations, estimation, when you start doing the derivative, the first thing you do in starting to introduce the derivative is, however you introduce it, is to make estimations of the derivative. And then you'll make tables and you say, well, it's getting closer and closer. Then you'll introduce some limit language, which is about just saying, well, what are the estimates getting close to? What are we actually estimating? And then you move on, and pretty soon you've lost the estimation idea, and you're always talking about limits. And good question? Or just pointing at the sky. That's good. Still there. So estimations are really important, and they carry on through the whole course. So if you recognize that as a theme, then whenever you come upon it, you say, okay, so what are we estimating here? All right. So first we're estimating derivative. But when you use the differential or linear approximations, you're doing estimates of the value of the function close by to a value you know, using the derivative to do that. So you're using the derivative to actually make an estimate. That's one of the great values of the derivative. And then mathematical modeling. So I was thinking about this morning, actually. And the history of the calculus goes back before the calculus. I think probably know that. But actually, if you want to talk about sort of the early work in the calculus, you might say, well, okay, Archimedes was doing some work that sounds like maybe stuff in calculus. He found the areas of parabolas, and he could find tangent lines to parabolas, and he was really good at all that stuff, but he wasn't good calculus at that time. And it was all geometry. So he only has one interpretation, it's geometry. That's all Archimedes is doing, unless you get to his physics. But we don't talk about his physics in the math program. So, it fell asleep. Wake him up. Okay. So, when we're talking about differential equations, we have that in our first semester. We're talking about related rates and implicit differentiation. Those, when you do the derivative of both sides in the implicit equation, all right, what you're left with is a differential equation. So actually, you've got a differential equation and you have the solution beforehand. The solution to the differential equation is a function possibly described implicitly that satisfies the differential equation. So when you do implicit differentiation, you're already starting to talk about differential equations. When you do related rates, you're starting to talk about differential equations, the rate equations that you're talking about, the relationships of those rates. Those are differential equations. Only you're given the answers when you start there. Okay, but the important thing is, looking at historically, is that the real person to focus on, historically, about calculus in terms of the three things I said. Right? The differential equations. Second one is estimation. Third one is modeling. So we haven't talked about the modeling yet. So the great person for thinking about math and modeling is Galileo. Because Galileo, working for the military-industrial complex of his time, was interested in cannonballs, in the motion of cannonballs. And that is the interpretation, that's the first modeling interpretation we're using in the calculus that's not geometric interpretation. And that's a very important interpretation, because the derivative there is interpreted as a rate, as the velocity. Okay, so we keep that in mind as we're going through the course. Whenever we interpret something about the derivative, we have two interpretations, a geometric interpretation, and we have an interpretation with velocity and motion. All right, that's the model. The basic modeling interpretation of rate is some kind of thing moving. It could be the temperature is moving or changing. It's that kind of thing that we're keeping track of. Okay, so we got this stuff about the derivative, and then what do? We interpret the derivative. We use the derivative to say things about something else. So if we know the derivative is positive, we say, oh, well, the function's increasing, or we say the graph is moving from left to right, a geometric interpretation, and we say something about the second derivative, we say that the object is accelerating, it's positive, it's decelerating, it's negative, and we say something about the concavity on the graph. All right, so we're taking information about derivatives and saying something about the original function. Well, that's what so we know something about the derivative, we want to say something about the function. So that's reversing the information. That's what differential equations is about. It's about reversing the information. If we know about the derivatives, what can we say about the function? The more we can say about the function, the more we have, quote, solved the differential equation. So when you're doing graphing and talking about velocity and acceleration, and interpreting those things, saying, here's the velocity, here's the acceleration, here's the derivative is positive, here's the concavity is such, we're really talking about information from the derivative getting back to the function. We're talking about differential equations. And we're making estimates because we don't know exactly how it's increasing. We're saying something qualitative about the estimate, not quantitative about the estimate. All right? And the modeling is always thinking about motion. Okay? Okay. So I was going to put a piece in here about reviewing about estimates with differentials, but here's the very simple idea, and maybe I'll put it on the board here for a second. And I like to think about functions not always with graphs. So I have a whole project about mapping diagrams. So I'm going to the mapping diagram here. So I'm going to put time here and position here as the variables on this diagram. And so here's a certain time, let's say time A. And I know the position at time A, that'll be f of A. So I draw an arrow like that. Okay? And I happen to know, at this time, I happen to know what the derivative is. So I'd like to know what's going to happen a little bit later at A plus H, or we call this dx if you like. That'll be H. All right, delta x or dx. And so I want to know what's going to happen over here. So what I know is, at this time, I'm at this position, and I look at my velocimeter, and find the derivative here, and I find, I'll just put here this little flag. Actually, I'd like to put an arrow there. I think of it like a vector at that point. But so I'll put in here, here's my derivative. So a typical example I give in class is I say, okay, so I know at time 3, I'm at 7, and my velocity is now 4, and I want to estimate where will I be at 3 and 1/10. And that's a question I gave in my exam yesterday. Last week to my Calc 1 students, and we haven't done differentials yet. We haven't done their estimation yet. But this doesn't take anything. This is a question that can be done by a junior high school student. Because what am I telling you? I'm telling you, at this time, I'm at this position, and I'm traveling at 4, whatever the units are, miles per hour, feet per second, whatever it is, all right? So I want to know where will I be roughly in 1/10 of an hour, or 1/10 of a minute, or 1/10 of a unit at a time. So what do? You take rate times time and add it to where you were. That's the differential. So if If I want to estimate where I am at 3.1, it'll be 7 plus 4 times 1/10. 7 and 4/10. That's where I estimate I'll be. That's all the differential is doing. All right? It's a very simple model. Here's where I am. Here's how fast I'm traveling. How much will I change in a small amount of time? All right? So that's the key idea, and you got the idea of rates, differential equation, because we're taking information about the derivative and using it to understand what happens with the function. That's what differential equation is about. We're making an estimate, and we have a model interpretation. All right? So that's at the heart of all of the course. The way I teach it, everything is related to that. When we get to the series, that's a whole other thing. But it all ties together. So I don't start my series with sequences. I start my series with Taylor's theorem. Because Taylor's theorem says how to make an estimate of a function based on information about the derivative, which is coming from a differential equation maybe, how to make an estimate of that. And you can use a model in context to make that like, okay, it's always changing at the same rate with exponentials and stuff. But I want to talk about the fundamental theorem of calculus. So here's the fundamental theorem of calculus. Well, there's two of them, right? All right. Now, when I learned calculus, I was unfortunate. I only learned one. I learned the calculus I learned was from Thomas.
Yeah.
The third edition, the famous third edition of Thomas. Some people don't even know what that means, but anyway, that's the classic Thomas, and that's what I learned from. And so I learned the evaluation form of the fundamental theorem of calculus. And it says if the function is continuous, and I'll say I won't bother with all the details there. Last speaker did a lot of the details. I'll just say it's continuous, and I have a function, the derivative is that, so that means that I can interpret this function as velocity. We'll get back to that. So this function has some other function that it's the derivative of, and that works for all x. Then, if I wanted to use integral, we'll get to the definition of the definite integral later, but the definite integral can be evaluated by evaluating the change in that function from a to b. It's the net change. So some people call it the net change theorem. All right, it's the net change. All right, we'll get back to it. The other derivative form, which I only learned after I had my calculus course, is very similar, although this one is even a little bit wild because this one defines a new function from the original function f, which is continuous. You define this new function g. It's the definite integral from a to t, so it depends on t of our function, and all that x dx is all this unnecessary notation, but it's very helpful. We'll see why in a second. Then g is differentiable function, and the derivative of g is f of t. All right, so those are the two main fundamental theorems of calculus. What I want to do for the rest of, I guess I got a half hour left. What I want to talk about for the rest of the time is how to make sense out of that from the interpretations I've given you. And the key to that is how you define the definite integral and how the definite integral fits into the themes of solving differential equations, estimation, and modeling. Okay, let's look at an interpretation of the evaluation form. Okay, so in the evaluation form, we've got a continuous function, and its derivative is it's the derivative of something, and tells us that the integral is going to be the net change in that thing. So here's the interpretation: g of x is a position function. Okay? Great. So the derivative of the position is the velocity. Okay? So we're going to get an interpretation for the definite integral. This is crucial. The definite integral from a to b represents the net change in the position of the object from time a to time b. So we want that, when we get to the definition of the definite integral, that should be the first thing we think about. Oh, the definite integral comes with an interpretation that says it's the net change in position. And that's the way we want to define. We want to get a definition for the definite integral that makes that, oh, that's the sensible way to define that. That's the number that we want to talk about. So that's the first thing, is to think about how we're going to define the definite integral so that the definite integral will automatically, in our mind, bring to mind a change in position, which will make this statement transparent. So that'll be a change in the way we think of the definition. The second thing is the derivative form, which is also Barrow's theorem. Now, I don't know how many people know Barrow. How many people have ever read Barrow's theorem? Or read Barrow? Yeah. It's great to read Barrow because Barrow actually has this result before there's any calculus around, although Barrow is finding derivatives. He knows how to find tangent lines, and he has some methods for doing it, but he doesn't have the symbolic notation that Newton does, and he doesn't have the same point of view as Newton. So Barrow's theorem is about you have a curve, you find its area function, you want to know the slope of the tangent to the area function curve at a certain point, and you find it's actually just given by the original function's position. It's a really neat proof, and the proof is very geometric. Barrow's not that interested in motion. Newton is very interested in motion. He's always moving. And I don't know if it just fell on him or something, but he's lucky. So for the function is continuous, and now we have this g of t. Now remember, we said we're going to interpret g of t as the change in position. So we start off with a function f is the velocity of the object at time t. G of t is the net change in position of the object from time a to time t. And so what's the derivative? So that's like, explain to my students is, well, okay, so I tell you the velocity. From the velocity, you figure out where you are at any time, solving a differential equation, figuring out where you are at any time. And then I ask you, all right, so at this time, what's your velocity? So I say, that's like asking who's buried in Grant's tomb. Right, I told you the velocity, then I told you how you found your position, then I asked you what was your velocity. So you're obviously going to get back to the original velocity. So there's nothing really super deep about this form of the fundamental theorem of calculus if you understand it and interpret it in the motion differential equation view. It's telling you what's obvious. And if the definition of the definite integral is appropriately motivated from differential equations, from estimations about solving differential equations in a context where the model is the motion model, then it will all make sense. So, this is, so some of the stuff I have here I have linked, and I'm going to, we'll come back to this, I think. But the motivation for the fundamental theorem comes from an estimation of a solution to an initial value problem, with visual and numerical estimation, with graphs and mapping diagrams. And I think we'll go on and we'll come back to look at some of this from my own materials that are online. All right, so first of all, estimating solutions to initial value problems. So what's an initial value problem? It's about a differential equation. So you're given the derivative. Y as a function of x. We're given its derivative. I usually like to think about that derivative being given first, so I call it p of x. So we're starting with the derivative, and I'm going to give it a name. It's some function of x. It could be a function of x and y. Actually, I talked about it as a function of x in my materials, but you pretty soon understand a function of x. But the differential equation could depend on x and y. That's the way the equations look when we solve the implicit differentiation problems in Calc 1. They're about, you get equations that involve the derivative as a function of both x and y. All right, now our problem is we have some initial condition, so the value of the function at a is given to be c. So the value of the function at a is given to be some number c. And what you want to do is to find exactly or estimate the value of the function somewhere else. Maybe close by, but maybe far away. If it's close by, the differential will get you through. You can make a quick estimate using the differential. If it's far away, you need some other technique. Because this differential only works as a pretty good estimator, and it works better the closer you are. That's the way that we estimate the derivative, with these small changes. So, the Euler's method is basically just a progression of estimates based on the differential idea, or the linear estimator. So, here's how it works. You start off with the differential equation with the initial condition, that's the f of a equals c. And we want to estimate or find the value at b. Now, if I had an antiderivative, if I knew the position function that was giving me this velocity, well, then I could just figure out what it was by plugging it in. But I'm not that lucky sometimes to be able to figure out an antiderivative, so I'm going to use estimates. The first step is just use the differential. In the second step, you make two equal steps. So if I wanted to get from 3 to 5, want to get from 3 to 5, 2 equal steps, so I go from 3 to 4 and then from 4 to 5. And each step, I would use a differential. But after the first differential step, which is the step of 1, I'm going to reset my derivative because I'm going to look at where I am, and the differential equation tells me what my derivative will be at that time and at that position. So I'll reset and do it again. And if you want to do n steps, you break the interval that you need to move into n's equal pieces. Why not use equal? Got no preferences one way or the other. Might as well use equal. Makes the computations easier because we're going to be using that dx all the time, that change. So you break those up. That would give you, if this were going from a to b, you take b minus a and divide it by n. You'd have n equal steps. And each one of those steps, you'd make one little step at a time, compute the derivative, take the derivative times the change in the step, add it up, and keep doing that. And rather than think about visualizing that, well, you can put it in a table, or if you like, you can think about visualizing it, make little steps here along the way on your mapping diagram. So, one way to do this is a systematic use of spreadsheets to make the estimation, and spreadsheets are really good for this. And you can use spreadsheets, you can use Excel if you want a commercial, you can use OpenOffice has spreadsheets, GeoGebra has spreadsheets, you can do GeoGebra. So there's all different ways you can get the spreadsheets, and each one of those will allow you to visualize what's going on along the way with a spreadsheet, either in a GeoGebra or an Excel. And I'm going to show you a little bit about that. I've got one set up here. Maybe it's not showing. Okay, so I'll move this over here. I'm not seeing it. Okay, so this is a spreadsheet in Excel, and I've got a differential equation here. So this initial value here is 0. That's A is 0. Value is C, and I'm using an interval of 2, so I'm going out to 2 here. And the differential equation is here, and let me show you what that is. So I'm doing, this is pretty easy, it's 2 times the x plus 1. Okay, so we all know how to solve that. And I use something that they know how to solve first, because what you want to see is that the Euler's method is giving you an estimate, and you want to know what the answer is. So you want an easy differential equation to start with, so you can check to see that this method is actually giving you a good estimate of the value you know. Because when you get the values you don't know, you want to have some confidence that what you're doing is actually working. All right? So I'm using 2x plus 1 for my differential equation. Can everyone see that? Okay, so 2x plus 1, so that's x squared plus x plus some constant. And the constant at 0, it's 0, so the constant is 0, so it's x squared plus x that we're doing here. So when we get to 4, we should get 4. We'll get to 2, because I want to estimate it at 2. That's what I'm looking for. The value I want to get for that estimate, well, it's 2 squared plus 2, so it should be 6. And with this estimate, I'm getting 5.6. Okay? So here's how it works. You've got the derivative here. That's our derivative. And then I multiply it by my, over here, I just multiply it by the dx, which is over here. It's a little bit over here.